So thanks so much for having me here, and thanks everyone for coming. And actually, I think there is a little more room to sit on stairs and so on, so people don't have to stand the whole time. So don't worry about making your way down. So first of all, I've just had a terrific day here today. I'm so excited about IDSS and what MIT has put together. I think it's really forward-looking. In fact, we're sort of thinking about trying to copy it at Stanford. So it was really great to see how well it's working. And I think my passion for this sort of interdisciplinary kind of program is really the same as the root of my interest in this topic. So about 11 years ago, I was invited by Microsoft to be consulting chief economist, where I mostly spent time on the search engine. And the reason they asked me to come was because I was an expert in market design and also data-driven market design. And so that was obviously very helpful for thinking about running an advertising platform where they didn't really have a lot of economics. So I thought I was going to go there and think about pricing and auctions. And I sort of did. But it turned out that that was really not the most interesting thing happening there. Instead, there was this really application that was really on the forefront of bringing together different disciplines to solve a real-world problem. And one of the very interesting things about it was that the search engine was mostly run by engineers and machine learning people. They were very sure that the tools they had would solve every problem. When I first started raising particular issues, people kind of didn't listen to me very much and thought I was a little strange, and it didn't matter how famous an economist I was. This is a search engine, and if I don't prove it, then it's not important. But then over time, I think together, the group of us solving these interdisciplinary problems realized that there's actually a lot of problems that don't fit squarely in the domain of prediction problems. That are very important for the real world. So things like, what would happen if I changed the auction, which is something we always thought about. What would happen if I raised prices for advertisers? Long-term versus short-term issues, equilibrium effects, and so on. And that many of these problems that we needed to make decisions about were really decisions. Like, what would happen if we did X, Y, or Z? And those are not in their core prediction problems. And even something as simple as the click prediction algorithm, which is sort of the heart of Google and Microsoft's money, the click prediction algorithm is used to score ads and decide which ads should be put where. And the real question that those click prediction algorithms were designed to answer is, what would happen if I took this ad out of position 3 and put it in position 1 instead? But it was being solved mechanically as a prediction problem, not a causal inference problem. And of course, it fundamentally is a causal inference problem. What would happen if I put this ad in a different position? And it's one that also involves extrapolation because you haven't seen every ad in every position. And so what we found was that by bringing in some ideas from causal inference, you could actually make these things better. But I would still say that even today, the Google and Bing systems probably could be further improved by further injection of some of the insights we've had from causal inference. Why did I not do that? Why has it not been done already? Well, part of the thing is that the traditional methods we use for causal inference and economics and econometrics were all designed for small data settings. And they were really all designed for a world where there's this one thing you want to know, and n goes to infinity, and you can kind of estimate it very well. And they were not, we didn't have a lot of algorithms that worked in imperfect worlds and without enough data to really answer questions perfectly. And so I think that kind of intersection is on the frontier of research today, and it's a really exciting research frontier. And so for a couple of years, I went out and I tried to get my econometricians friends to work on this, and I gave talks like this, and I said, here are all these great open questions. And I couldn't convince even my husband, who's also my co-author, I couldn't convince him to work on it. I couldn't convince anybody to work on it. And so I finally started trying to work on it myself. Then actually, my husband started working a day a week at Amazon, and then he also came home and said, oh, wow, there's all these interesting questions we don't know the answer to. And I'm like, yeah, I told you so. And so now there's actually a whole collection of us working on this. Whitney Newey, he's teaching now, couldn't be here, but I was just meeting with him, and he was talking about this conference we just went to together, and there were 30 papers presented at the conference from all different disciplines about the intersection of machine learning and causal inference, and it's a really, really exciting area. And so I'm going to talk about a number of different papers today. You can check out my archive.org page for most of these papers. So just to start with, because I know people are coming from a lot of different perspectives, let me just start by defining a causal inference and kind of making precise what the problem is we're looking for, and then I'll talk about a bunch of solutions to the problem. So the potential outcomes framework is a framework where we think about seeing a set of subjects, let's for simplicity make them IID, and each subject has a feature vector or a covariate vector, their characteristics, and we think of these as being like unchanging characteristics of individuals. An outcome, Y, and W, which is a treatment assignment. So you can imagine that W is something like, did you get a drug? Or which email did I send to you? Or which ad did I show to you? Or did you see an ad? Those are the treatment assignments. And so the potential outcomes framework basically says that a good way to think about the problem of treatment effects and causal inference is to say that for each individual, there's actually associated with you a vector of potential outcomes. These are the outcomes that you would have had with different treatment regimes. So I can imagine some of you had coffee right before you came here, some of you didn't, but each of you has a set of potential outcomes for how alert you are if you did have coffee and if you didn't have coffee. Now, just looking at you, of course, I see you with coffee, so you got a nice espresso there. So you're drinking your coffee, so I never know how much you would be smiling at me if you hadn't had the coffee. And so one reason, this framework we've been using in economics and statistics for many years, it's not been as commonly taught in machine learning. And so it's actually important to sort of start with this to really even understand why is there a problem at all. In my early days at Microsoft, I spent a lot of time arguing with machine learning people who were just like, I don't understand what you're talking about, Susan. Like, all problems are prediction problems. Why is your problem different? And so, one way to think about it is that, there's a missing data problem or a missing label problem that and it's a fundamental problem that for each of you at a point in time, I can't see you in all the different states of the world. And so then the question is, how could I ever draw inferences about you without coffee? Okay? And of course, it should be immediately clear that you cannot draw inferences about who you are without coffee without some additional information or assumptions. And those assumptions could be very simple assumptions, like I randomly assigned you to coffee, in which case that's an easy to describe, but that's still an assumption about the data generating process, that your treatment was not dependent on how well coffee helps you, for example. So this is the fundamental problem. And actually going back even before this framework, people have been writing down demand functions in economics. So we write down something like, what's demand as a function of price? You can think of that as a potential outcomes function. And the object is, how much would I sell if my price was 100, my price was 99, my price was 98, my price was 97. So that's the potential sales of your firm depending on different values of the treatment. And so one reason economists were so focused on causal inference from the very beginning of our empirical existence is that if you actually just take a data set out there, like a data set of prices and quantities, and you try to use prices to predict quantities, you will usually find that higher prices predict higher quantities. Which of course is nonsensical from a causal inference perspective, but it's perfectly plausible from a predictive perspective. So if I was a hotel and I wanted to say, gee, how full do I think the hotel next door is? If I used historical data, like I had somebody sit outside and count the people for a couple of years, once a month, and then put a data set together, and I put that together with prices from hotels.com, I would probably find that when the prices are high, the hotel across the street is full. So if my predictive question is, given price, is the hotel full or not? A positive relationship is, of course, exactly the right answer, and it's what you would find with a great machine learning method. However, if your question was, what would happen if I shifted my pricing policy? Well, that's not the same. Increasing your price won't cause you to sell more hotel rooms. And so because you cannot get sensible answers out of many economic models, we don't think of this as rounding error. We think of this as a first-order problem. So some of the things that we try to look at in this context, we might look at the average treatment effect, which is the expectation of the difference between your outcome if treated and your outcome with control. We can also think about the average treatment effect on the treated. So we can say, well, of the people that were treated in my current group, what's the treatment effect for people like the people who got the treatment? And then finally, we can talk about the conditional average treatment effect, which is that treatment effect conditional on covariates. And this last thing is something that one of the first problems I started tackling in this area. And it's really kind of course, very core to the benefits of machine learning. Machine learning are great at doing personalized prediction. And so wouldn't it also be great at figuring out personalized treatment effects? And wouldn't that also be great then in figuring out personalized medicine and personalized ways to decide which ad to show you and which email to send you? Now, of course, again, you might think that this is already a solved problem in industry because, of course, if you just pick up the newspaper or think about what's happening to you on Amazon, you sort of assume that what's happening to you on Amazon is that they have already solved this problem and are using it to allocate things to you. But it turns out that even the tech firms are often not doing that. They're allocating to the people who are most likely to click, which is not the same as the people for whom an ad would be most effective. And so the tech firms themselves are now catching up with the causal inference approaches to really solve the actual problem. So whether you click is, of course, associated with whether it's good for you. If you don't click, it's probably not good for you. So solving the prediction problem gets you 80% of the way there. But it won't help you fine-tune and get exactly the right answer. Because the business question is actually, I want to figure out the best treatment for you personally, not just predicting who will click on the ad. And so just to, here's a little cartoon that kind of illustrates all of this. My stomach hurts. Maybe it was a bad tuna I had for lunch, but I'll never know. I don't know what my potential outcome was. Maybe I could estimate whether it was the tuna by looking at a sample of other people who had tuna and didn't have tuna, but that's actually a statistics problem. Okay, so without any further assumptions, that's actually a theorem that you cannot estimate any of these things. And so, again, this is something that in econometrics, we've thought about questions like this for a long time. We use words like identification. And what identification means is, could I answer my question if I had infinite data? And so when I used to argue with my machine learning colleagues at Bing, we would get very confused because they'd be like, oh, well, if I just had more data, I could answer this question. But going back to the hotel room example, I could have lots and lots of people counting and prices in hotels, and I will still find out that higher prices predict higher quantities. I need something else, like some sort of exogenous variation in the prices or experiments to figure out what would happen if I changed my price. So one type of assumption, and this is going to be a starting point for some of the stuff I talk about today, is something called unconfoundedness. And the unconfoundedness assumption basically says, conditional on the things I observe about you, your treatment assignment is as good as random. So it's a little bit, it's like saying we're almost as good as if we had a randomized experiment because of the things I observe about you. And there's a huge literature over decades arguing about the validity of this assumption, the estimates that come out of this assumption, and different methods for solving problems under this assumption. One thing that's nice about the new tech world is that we actually have algorithms that, by definition, satisfy this assumption. If you think about the treatment assignment you get on Amazon, by definition, an algorithm cannot use an unobservable about an individual to make assignments. An algorithm takes inputs and produces outputs. So, and some of these algorithms are random, and some of them are not. But actually, many of the tech firms do induce randomness. And so, so a lot of data that's generated by tech firms satisfies this assumption. Conditional on the inputs to the algorithm, there was then some randomization, and it might be an advertiser's budget constraint running out, and it might be the server that you pinged, and it might just be that you explicitly are exploring, but you're going to have this assumption satisfied almost like by construction. So I think it becomes a more interesting and palatable assumption in the digital world. Okay, so in this massive literature, which has gone on for decades and has hundreds of thousands of methodological papers and empirical papers and so on, if you're not from the literature, it's kind of hard to summarize all of that in 5 minutes when I also want to tell you about my new research. But let me kind of paint a picture of that literature and give you a sense of how it has proceeded. So we can think about different designs that might allow us to answer a causal question. And then we can also think about different questions you might answer under those designs. So the simplest design is a randomized experiment. And now, more recently, we have tech firms running bandits, which is like online exploration, which are generating randomness in a lot of the things that happen to us online and on mobile devices. Then unconfoundedness is a world where the treatment is as good as random, conditional on what you observe. Beyond the tech firm examples, it might also be satisfied if, say, Like a judge has to make a decision about you, and we see the same screen of information the judge sees before they make a decision. So we see everything that goes into a decision-making process, and it may not be a formal algorithm, but we can estimate the policy rules that are being used. And then something that's much less familiar and much less widely used in machine learning is instrumental variables. And it's actually a workhorse in economics. Josh Angrist is here from the economics department, who was a pioneer in doing work on instrumental variables along with Hito Imbens, my husband. And instrumental variables is basically, it's like a natural experiment. So one of Josh's early examples was trying to figure out the effect of military service on your later labor market outcomes. And so when in the Vietnam War, people got lottery numbers that determined whether or not they would get drafted. So it wasn't a designed experiment, but it was a natural experiment. Now, there was not a deterministic mapping from your lottery number to whether you actually went to war. Like if you had a sore heel, you might not have to go to war. But there's a probabilistic relationship, and if you can estimate that relationship, then you can uncover causal effects. So you could think about things like, for hotels, things like changes to the input costs, so maybe changes in minimum wage laws or union activities or other types of things that affect hotel costs, which might affect hotel prices in a way that's not related to the potential outcomes. Another type of design that we use is regression discontinuity. This is a design where you might compare two families that live on either side of a school district boundary to see to get at the causal effect of the school that they went to, as an example. Or you can look at people who lie on either side of an eligibility threshold. And we're getting more and more interesting examples of being able to do that as we have these structured school choice programs. Another type of setting that allows us to learn about causal effects is panel data. So in panel data, I might see the same units over time. Like say I could watch states over time. And it might be true that the states that adopt minimum wage laws look different than the states that don't adopt minimum wage laws. But we can look at what happened to these states before the adoption of the minimum wage law and potentially use other states that had similar time trends before to come up with a counterfactual of what would have happened to the state if it wasn't for this minimum wage law. And Alberto Abadi, of course, is a pioneer of synthetic controls, which is one method to use this. And I would say, actually, in my tech firm experience, using kind of panel data and the types of things that I just talked about was one of the most common things we did in practice to answer business questions. This set of advertisers got this particular treatment, and we're going to find control advertisers. Or I just used it for another example. I was looking at the effect of Google News on the news people read. And so I had a set of people who were Google News readers, and I matched them up with, from millions of users, I found the users who were most similar before Google News got shut down in Spain, and I could then get the causal effect of taking Google News away on the news that they read. So this is another common thing. So these are all ways that we identify, and this is sort of descriptions of how, if you had enough data, you could actually learn a causal effect, even if you didn't run a randomized experiment. Then about each of these things, we can do things like estimate average treatment effects, something called local average treatment effects, again, conditional average treatment effects, so conditional on your observables, what's your treatment effect? We can estimate optimal treatment assignment policies. And those are very closely related questions, but not the same. If I know how your treatment effect goes with your x's, that's not quite the same statistical question as estimating what is the best policy assigning from x's to treatments. They're very close, but not exactly the same. We also want to do things like structural parameter estimation. So I want to estimate how sensitive are you to prices. That's what we call a structural parameter, a price elasticity. And we also might want to do things like just ask, well, what heterogeneity is there in the data? So these are all different questions. So now that I've laid out where we are starting from, or where I was starting from when I came into machine learning, the agenda, very simply stated, is to redo everything that we did better using machine learning. And I basically have entries in all of these categories at this point, and so do a number of others. There's a small group of us. A couple years ago, I could talk about all of it in 1 hour. Now there's a burgeoning set of groups. So there's a group here at MIT, Viktor Chernozikov and co-authors. There's a group at Berkeley, Jasikan and Ben Yu, more from the stats poli-sci side. There's our group at Stanford. And there's a few other groups emerging as well that are all attacking this problem, these set of problems. Now, most of the energy went into average treatment effects and conditional average treatment effects under unconfoundedness. That is the problem that has like 10 or 15 papers and a bunch of dueling methods already. Some of these other problems only have a few entries to date. Being at the search engine gave me advantage. I got to be early and tackle a lot of these things first, but I'm expecting that each of these will have multiple entries, and this will be kind of a fairly full research agenda. I'm already teaching a quarter-long class at Stanford, and I already can't cover everything. So what I'm going to do today is then tell you now, spend the rest of my time, I've laid this out, talking about a few of the specific algorithms that solve a few of these problems. But I won't be able to talk about all of them today. And I no longer can survey everybody else's work either because it's long. I did give a course for the American Economic Association just a few weeks ago. And on the American Economic Association website is my video from a day and a half of lecturing about this, my reading list, some tutorials, R scripts, data that allow you to run almost all of these algorithms. And if you can link to it from the AEA website or just email me and I'll send you a link. Okay, so let me first talk about average treatment effects with unconfoundedness. So as I mentioned, now there's multiple teams attacking this problem, and if Victor hasn't talked about all of his stuff, you should check it out. He's here at MIT. I'm going to talk about my entry in here. But let me give you first some of the themes that have come from this literature already. I think the early theme is that prediction is not equal to causal inference. And we demonstrated that very clearly in this setting. So just to explain that theme, I can talk about the double Lasso papers by Victor and co-authors. So the idea of prediction, suppose I wanted to use, say, a predictive model to understand the effect of a treatment on your outcomes, but that treatment estimating that treatment effect is subject to confounding. That is, there's some characteristics of people that both made them more likely to get the treatment and more likely to have a high outcome. So, maybe there's some of you whose offices are nearer to a coffee shop, so you're more likely to go get coffee before here, but it's also a better MIT department, and so you're smarter. Then there would be a correlation between coffee. Then if I just looked at the impact of coffee, I would inaccurately conclude that part of that effect of coffee is really just what came from being in a department near a coffee shop. So that's... okay, well, not a problem here then. So if you just ran the easiest thing you could do is just run a predictive model, like say something like a Lasso. You could throw in the treatment assignment and all the X's, and you could say, oh, Lasso is really smart. It's going to pick up all the X's that are important. But the problem with that is that for the perspective of getting a treatment effect, I don't just want to control for X's that are good at predicting Y's. A Lasso model wants to predict. It wants to be good at predicting Y's. So if it has to choose between two X's, it'll choose the X's that predict outcomes rather than the X's that are super important to control for, which are X's that are correlated with both the treatment assignment and the outcome. So that's a different objective. So a very simplistic thing, which actually worked surprisingly well, that was one of the first things that, that Victor's team proposed, was the double Lasso, where you use Lasso as a way to select variables, X's that affect your treatment assignment, and you separately use Lasso to select X's that affect your outcome, and you control for both of those. But of course, this is clearly not optimal. This is just a heuristic. And so the subsequent literature then has gone into better performing and more sophisticated methods that really address the problem at hand, which is that you want to control for confounders. Some other themes that have come out is that actually, using what we knew from statistics and econometrics is very helpful in guiding algorithm development. Another theme that's come out that's very important is that you want to often use sort of two-step methods where you residualize out nuisance parameters. So you first run predictive models and try to explain as much as you can with the predictive models, and then you do something more tailored and specialized on the residuals from those models. And that turns out to have a really big performance improvement. And then finally, the choice of methods actually just depends on how complex your problem is, and different methods might work well. In simple problems, models with more structure will exploit that simpleness and will work very well. More complicated problems may need more complicated methods. So we know from the econometrics literature that there's actually a whole bunch of different methods that are all work well in the small data setting. So one thing you can do is something called propensity score weighting, and that basically means that you estimate the probability that you got a treatment as a function of your covariates, and then you reweight the data so that the data has the distribution of the average individual. So like I might have more people with coffee who come from a certain department, so I'm going to downweight those people. And I might have less people who have coffee who come from a different department. I'm going to upweight those people. And that weighting can solve this confounding problem. An alternative way to do it is I just estimate the outcome function. So I say I'm going to estimate the mapping from x's to outcomes, and if the people I saw with coffee are different than the people I'm interested in, I'm just going to model how they would be if they had different characteristics. And then there's something called doubly robust, which combines both of those, and those things tend to work well. So a doubly robust method, I can now write this in notation. If you're trying to figure out what would have happened to the coffee drinkers if they hadn't had coffee, what I need to do is the counterfactual outcome for the coffee drinkers in the absence of coffee. And so if I have a model that relates their characteristics to their outcomes, I can construct that with just this first term here. So I can say, here is the characteristics of the people who had coffee, but I could estimate what would their alertness be if they had been without coffee. So the beta hat zeros, that's the prediction of what you would have gotten among the people who didn't have coffee. So by estimating this model, I can say, I can take all the characteristics of the people that I saw with coffee and adjust to what would happen if they didn't have coffee. Now, if they're very different, that extrapolation might be very far. So I might have a cloud of people over here and fit a line through them, but if I want to project them all the way over there and I get the slope of the line wrong, well, I might do a very bad job with prediction. So doubly robust says, well, let's adjust that by reweighting. And so in particular, I run a regression of the outcome on the covariates, and then I take the residuals. And I adjust my initial prediction by reweighted residuals. And it turns out that this is doubly robust, and doubly robust in the sense that if I get either the slope wrong or I get the betas wrong, but not both, I'll still get the right answer. It's a little bit magical. So I only have to either reweight the people properly or estimate my model properly, and either one of those will give me the right answer. Why is that? Well, if I just look, if I get the outcome model right, then this prediction is great. This is just telling me what would have happened to these people if they were in the control group. And furthermore, this will have mean 0, so everything's fine. These gamma hats are going to be the weights. If I just rearrange the same expression, this is the same expression, just rearranged. I can see how I'll be okay if I get the weights wrong, the model wrong. If I get the model wrong, then that won't matter if I've reweighted the data properly. What I'm trying to do is reweight the data to make the control group look like the treatment group. And if I reweight that properly, then I will have succeeded in making the control group look like the treatment group. And so it doesn't matter what the betas are, this will be 0. And then over here, I'm saying, oh, now I'm going to make my predictions just based on reweighting the control group to make them look like the treatment group, and that's another way to get the right answer. So this type of method has been relatively successful, and it has these nice properties. So then the question is, what would you do, given that this setup, how would machine learning help? How would we do a better job with this? And so there's kind of two obvious ways that it could help. The simplest thing and the most naive thing, and this is where a few people started, is, well, let's just use something like Lasso instead of ordinary least squares to try to fit these betas, to try to fit the predictive model. And then let's also use machine learning to fit the weighting functions and plug those in and see how that works. Now, in principle, this works, and it probably works better than what we used to do. But a big problem with that is that these weights, this is the propensity score. This is the probability of being treated as a function of your x's. If I use a big fancy machine learning model, that's likely to be a bit noisy, and I'm also likely to get extreme values. So I'm likely to say that a lot of people either have zeros or ones. You were very likely to get coffee, or you were very unlikely to get coffee. And so the objective of the machine learning model, which is just as to fit this, is different than the objective we're going to use it for. We're going to use these as weights. And we really don't want to have crazy weights floating all over the place, because that'll totally screw up my estimates. So, and then from a formal perspective, when you do the statistics, just plugging in doesn't necessarily have the properties you're looking for. So what we do in our paper is we say, let's compare what you get from a double robust type of estimate to the truth, and let's see what the difference is. And this is the difference here. So we can express the mistakes we make as the product of two terms. One is the part where we get the model wrong. So we have an inaccurate prediction of how the x's map to your outcomes in the control group. And one is that we get the weights wrong. And so what our method does is it says, let's actually attack this problem, not with an estimation method, but with programming. So if our goal is to get balance correct, rather than estimate a probability and then divide by it, why don't we just directly try to find weights that minimize the imbalance? So you might think, why didn't you think of that to start with? Well, in the small data world, we imagine n went to infinity. We have a small number of x's, so it was natural to think about just estimating all your quantities and plugging them in. But in the big data world, I can't estimate that well, and I might have more x's than I have observations. And that function might be kind of complicated. So then it becomes a really bad idea to try to estimate something and plug it in. And instead, we just use a quadratic programming to try to find the weights that minimize this imbalance. If there's more covariates than observations, I won't be able to do it exactly. But we prove under certain conditions that you can make this work very well. And so what that's going to do is allow us to then, say, use Lasso to estimate these things, and the product of them will give you an efficient estimator. And actually, the estimator is just as good as if you knew what the model should have been to start with. And so it performs quite well. And so the thing that's really novel about this is that it's breaking away from a world of like estimating things and plugging them in, and just tackling directly the problem that you're interested in. And as a result, I don't have to make any assumptions about the smoothness of this, or how hard it is to estimate, or it doesn't have to be sparse, it doesn't have to be anything. I just need to have the probabilities be interior, which is something we called overlap, and then it'll work. And so the theorem is that if the outcome model is sparse and we estimate beta using Lasso, then this estimate has rate 1 over square root of n, which is basically what you could get if you knew which covariates were important to start with and you controlled for them. And let me just skip over that. So, so summarizing, what we did was we put together the ideas from doubly robust small data causal inference with some ideas from machine learning. And here, actually, it wasn't, we use Lasso on one part, and there's other parts of machine learning that have just worked on programming and balancing weights, and we put those together for a higher performing estimator. OK. So let me now move on to the second topic that I want to cover today. And this is low-dimensional representation of the conditional average treatment effect. And so this is a little bit subtle, and actually the literature itself has not been good about separating these things out. But basically, now the conditional average treatment effect problem is, I want to know for each of you, given your covariates, what's your treatment effect. But that's a very complicated object. In a minute, I'm going to show you a paper where I show how to estimate that and make it asymptotically normal and beautiful. But in practice, it's very hard to estimate. If I have 100 dimensions of covariates and 1,000 observations, I'm never going to be able to fully estimate the function that maps your covariates to treatment effects. So in things like medical studies or field experiments we run in economics, we might want to ask about conditional average treatment effects, but we know that we can't really estimate everything that we want. So we want to find something in between. And so I've started calling this moving the goalposts. This term has been used before in economics for similar ideas. The basic idea is, instead of trying to understand fully the treatment effect heterogeneity, I'm going to ask a simpler question, and I'm going to ask a question to which I can get a perfect answer. Perfect from the perspective of getting, say, estimates that are unbiased, that are asymptotically normal, that have valid confidence intervals. And I should say that for those of you from machine learning, you might not care about those things, but for medical experiments, even for A/B testing platforms and tech firms, understanding that the statistical reliability of your estimates is very, very important. In a longer lecture, I talk more about why that's so important. Here, maybe let me just flag a key point, actually, that I should have said earlier, which is that machine learning methods, you don't need to worry about theory because you have a test set. Machine learning methods, your goal is to predict. I can hold out a test set. I've got a ground truth. I can see how well I predicted. Bing. I don't need theory to tell me whether it worked because I can just hold out a test set and see whether it works. So you've defined yourself to have a fairly simple problem. In the canonical, simplest machine learning case of telling cats and dogs, I just hold out some images and I can see whether I got the cats or dogs right. And I can compare algorithms using a test set. For causal inference, even if I have a holdout test set, I don't see for any of my individuals what their causal effect was. So figuring out what is the target is a super important question. And it's one of the main reasons that you can't just immediately apply machine learning off the shelf for causal inference problems. It turns out that under randomized experiments, it's not too hard. And so that's the part of the point of one of the papers I'll show you now is how to solve the problem of not being able to directly observe your goal. Okay. So some of the themes out of this literature are that we're going to try to find simple interpretable representations, and further, we're going to really focus on sample splitting, or what we call honesty. So if we're trying to get valid confidence intervals to say, here's an estimate of a treatment effect, and I want to say that, put a confidence interval around it that's centered on the truth, it's really bad idea to use the same data to do your data mining and to estimate your effects. And so very simple ideas like sample splitting are crucial. And I'll try to show you convince you of that with some examples. One other thing about the interpretability. So a simple model is not necessarily an interpretable model. So if I say run a lasso and it selects 3 covariates, but it zeroes out some others, in economics, we call that omitted variable bias. So if you have parents' income and parents' education, Lasso might put in parents' income but not parents' education. It would be a huge mistake to look at the Lasso output and say, parents' education is zeroed out, parents' income is in, therefore parents' education is not important and parents' income is. That's a complete misinterpretation of the results, because just because it's zeroed out doesn't mean that it's not important. It's just that 2 things are highly correlated and the additional information of the second one was less than other covariates. So people often take something like a Lasso and say it's interpretable, but I would say it's misinterpretable. And what you really need to do with these predictive models is say, all right, here are the people who are predicted to be high and these are predicted low. They're different in both parents' income and education. Just because my model selected one is not a reason to say that it's not important. And I think this is going to get, this mistake, I've already seen it made like 1,000 times, and I'm going to see it made 1,000 times more before social scientists fully ingest all of this stuff in. Okay, so the causal tree, this is actually my first paper in this whole area. It's the simplest paper. I was actually kind of embarrassed of it in the beginning, but it's the one that's gotten by far the most cites because lots of people are actually using it in practical applications. So somehow, even though my later papers have lots more fancy theory, sometimes being practical is helpful. So the motivation is that we might run an experiment, and we don't know in advance where the treatment effect heterogeneity will be. We would like to use the data to tell us, but the problem is ex post data mining. So even tech firms have rules that you can't take your experiment that you ran and then go back and say, oh, it worked for these people and not those people, and use that to ship your experiment. And the reason is that, of course, you can always find some group of people for whom your treatment worked. And so if you let the researcher just go off and search for some group of people where the treatment worked, they'll always find someone. But if you ran the experiment again, that group might not have good effects anymore. So we want to have a machine learning driven way to find heterogeneity, but one that gives you valid p-values and reliable results. And so what we'd like to allow the researcher to specify a set of covariates in advance, but not have to specify which ones are important. We also want to just understand the treatment effect heterogeneity because that might help you. Like if you know the drug works for these people and not those people, that might help your future science. If you know your algorithm at Amazon works well at recommendations for this group but not that group, then you would tell you how to fix your algorithm. So the causal tree method is basically building a regression tree that's optimized for causal effects. So machine learning people like regression trees, that's so 1980s. Like why wouldn't you build a neural net? But part of my point is I'm going to use the regression tree not to get the most personalized predictions, but rather to come up with a set of groups, of subgroups. So I'm basically going to use the regression tree algorithm as a way to move the goalposts to tell me a set of groups which are defined to be different in terms of their treatment effects. And then I'll use a second sample to estimate those treatment effects and get reliable standard errors. So what we're going to do is find a partition of a covariate space and estimate the causal effects within leaves. Machine learning methods are typically going to optimize for mean squared error of the outcome, but the mean squared error of the treatment effect is not observed for every individual. But we show, especially in the randomized experiment case, it's not too hard to estimate the mean squared error of the treatment effect. So I didn't write down all the math on the slides, but for those who are interested, what I'm interested in is the true latent treatment effect minus the estimated treatment effect squared. That's the analog of the mean squared error. But I can, even though I can't observe that because I don't observe any individual's treatment effect, on a sample, I can estimate the mean squared error. So instead of targeting like a simple average of observed mean squared errors, I'm going to come up with an estimated mean squared error on a test set or on the cross-validation set. And so we show in the paper, what good. We actually look at a couple of different ways to estimate and find a target that works well. Another thing that we do is because we're planning to sample split, we're going to use one data set to find the leaves and another data set to estimate the effects. We change the criteria to anticipate that our estimates will be unbiased. So usually there's like a bias variance trade-off in your mean squared error, but because we're going to take the leaves and then take a new sample to estimate, the effects that we're interested in, the treatment effects within the leaves, will be estimated in an unbiased way on a new data set. So that changes the mean squared error criteria because your bias variance trade-off changes if you're anticipating re-estimating your effects in a new data set. And we also show that that matters. And so this is really illustrating a theme that this is the simplest incarnation of it, but this theme spreads across this whole literature on machine learning and causal inference, which is that you need to think hard about what you're optimizing for. And the way that you change the machine learning algorithms is partly in telling it, no, I don't want to predict Ys. I want to do something else. And then you change your algorithms to optimize for the something else. Sometimes that's easy. Sometimes it's hard. It depends on the setting. OK. So this is just from a table from one of our, from the PNAS paper. And so here we're trying to show the difference between adaptive coverage of confidence intervals and honest. And again, just to be clear, what we're doing is we're dividing the data into leaves, and then we're going to estimate treatment effects within the leaves. And then we're going to construct confidence intervals for those. And of course, because we're estimating treatment effects within the leaves, this is just sample average, so the confidence interval construction is very straightforward. But if we use the same data to choose the leaves and estimate the treatment effects, the coverage of 90% confidence intervals is pretty terrible, while the coverage of 90% confidence intervals for honest estimation is perfect. And it will always be perfect. It will be perfect if you have 100 observations and 2,000 covariates. Because we're using one data set to make the cuts and another data set to estimate the effects. So there's no reason that your confidence intervals would ever be wrong. In addition, the criterion is going to ensure, just the way that you optimize the trees, is going to ensure that your leaves are big enough to get low variance estimates. That's part of the mean squared error criterion. We'll do that for you. So this is an example. I applied it to an experiment I ran at Bing where I re-ranked search results. I took the first result and put it in position 3, and the position 3 result and put it into position 1. The features are all classifications of the query. The average treatment effect was about minus 0.135. So you went from getting clicked 25% of the time to getting clicked about 12% of the time as a result of getting demoted from position 1 to position 3. We found that, and so this is kind of what the trees look like. It puts the data into subgroups according to the covariates. And we see here, this is a pretty big treatment effect. It's minus 0.22, so you're losing a lot of your clicks. These were queries that were categorized to be Wikipedia reference, high match, which basically means they were informational queries. On the other hand, this treatment effect was almost 0. These are ones that were classified to be good matches for celebrities and images. Basically, like people searching for those things maybe weren't going to click on anything anyways. They just wanted to look at a picture of the celebrity, and so there was no treatment effect. And so we can get that heterogeneity. Another big point I want to make out of this for social scientists is that I had hundreds of thousands of observations here. What here I have tables with adaptive estimates and honest estimates. So adaptive is when you use the same data to make the subgroups and do the estimates. Honest is when you use different samples to do that. And I have hundreds of thousands of observations and only 20-odd leaves. So you'd think that that's enough so that biases from using the same data to choose your groups and estimate your effects wouldn't be a problem. Because the problem is like overfitting to outliers. Like if you have a super high treatment effect, I'm going to build a group around you. But with thousands of observations in each leaf, you'd think that that effect would go away. But what I see is that the effects are more extreme, even in this case with tons of data. So the adaptive estimates are further away from the mean, which was minus 0.135, even in cases where there's thousands of observations in each leaf. And actually, these are the variance of these estimates relative to the mean is 2.5 times the honest estimates, which is saying that even with hundreds of thousands of observations, this is a problem. So the message to social scientists is when you use machine learning methods, your idea of n versus the number of covariates or parameters should be an order of magnitude different. One way to think about it is I had a robotic research assistant try billions of specifications to come up with these leaves, and my robotic research assistant is better at finding spurious stuff than a human research assistant. And so my results are that much more likely to be completely invalid. So you really just can't look at having thousands of observations per parameter. I believe you really need to do sample splitting and have honest estimates. OK. So now let me move on. That was kind of a moving the goalpost paper. And so again, instead of figuring out generally what is the best personalized estimate for you of your treatment effect, I divided hundreds of thousands of observations into a few groups. So I moved the goalpost, and I get very correct answers for those goalposts. But of course, if you're a patient and you're on the edge of one of these leaves, you don't want the best estimate for the leaf. You want the best estimate for you. This is a harder problem. And it's unsolvable in some data sets. But nonetheless, let's think about how we could attack that. So there's fewer entries into this category yet, partly because the problem is hard. And I'm putting up entries that have theory associated with them. So Knn, k-nearest neighbors, is a method that has theory associated with it. And then two methods that I've worked on, one is which a generalization of the other, use random forests to try to answer this question. And we're able to prove that using a modified version of random forest, we can actually get valid estimates of your individual treatment effects, as well as asymptotic normality and confidence intervals around those, which is what social scientists and medical research might want for their publications. So some of the themes from this literature, one is that one of the things we discovered between paper 1 and paper 2 was that instead of thinking about random forests as just a predictive method, I can instead think about a random forest as a way to come up with a weighting function for my data. And it's a way to figure out who should be neighbors for you. So if I think about wanting to estimate your treatment effect, I could try to say, all right, I'm going to find people who are just like you, but you're a very complicated person, and so it might be hard to find someone who's just like you in every dimension. But with a kernel estimator or a nearest neighbor method would try to find someone who's like you in every dimension. What random forests are is what you can think about random forests as a way to figure out who your neighbors should be and which covariates are important to make neighbors. And so that idea allows us to actually apply random forests to all sorts of algorithms. Anything that could be estimated by maximum likelihood or GMM, we can come up with personalized estimates using random forests as a weighting function. And we still have the big problem of tailoring the objective to the problem. So we want to figure, if we're estimating a parameter, we need to figure out how to point the machine learning guns at the parameter of interest for us, not at a predictive parameter. So a baseline method for personalized treatment effects is the Knn Matching Estimator. Again, I can take Alberto and I can find people who are like Alberto. Of course, Alberto has done a lot of great work on matching estimators. So people who are just like him who are treated, people who are just like him are controlled, take the average of the difference, and that's my estimate. We want to, instead of that, replace that with random forest as an adaptive nearest neighbor matching algorithm. So just to think about comparing KNN to random forest, KNN would say, I'm going to take people who are nearby you kind of uniformly. What the random forest is going to do is it's going to construct a bunch of trees. Each tree will be a partition. And then I can think about taking the treatment effect estimate among people who are in the same leaf as you, which they might be nearby you in some dimensions and far away from you in other dimensions. And if I use a causal tree, that is, if I use a tree like the one I just showed you that optimizes for treatment effect heterogeneity, then I will put people in the same leaf if they have different treatment effects. So we make a trees into a forest by subsampling, taking lots of different subsamples and building different trees, and then I can average up the treatment effects, and that will be my estimate of the treatment effect. So it turns out that the off-the-shelf random forest is lovely, and it works really well, and it'll get you 95% of the way there in a lot of contests, but it's not actually, the output is not asymptotically normal, neither for prediction nor for causal inference, because it's a machine learning algorithm. It has a bias-variance trade-off, and so on. But what we show is that if we modify the forest in a particular way, we can fix those problems. And actually, this is a kind of an unusual case where we end up with a method that can outperform the traditional method even for prediction tasks. So this little fix, it turned out the fix wasn't just trading off mean squared error and buying us good confidence intervals. It actually sometimes improves both, although I don't have a theorem about that. So what do we do is we use honest trees instead of adaptive trees. So the key about the random forest is that we're going to average lots of different trees, and the trees will be different by using subsamples. So we say, well, hey, if I'm going to take a subsample, why should I use just one sample to build the tree and make the estimates? Why don't I instead take two subsamples? Use one to build the tree, use the other one to make the estimates. And that way, if Alberto has a super high treatment effect, I'll find all the people just like you. I'll put Josh in your leaf, and then you have a really high treatment effect. He's kind of a dud, but I'll stick him in your leaf, and together this leaf will look like it has high treatment effects. But then if I go to another sample, economists who work on causal inference, that subgroup won't actually be especially good in the new subsample. And so I'll appropriately find that when I fit a leaf around you, that was spurious. Okay? So that's going to fix the problem. So what we show is that if we use honest trees, and we have to make deep trees, that's another thing, so the leaves have to get small, then the predictions from a random forest using these double sample trees or these honest trees will be asymptotically normal. Then as a corollary, we can actually apply this to estimating average treatment effects under unconfoundedness as well. So just to show the importance of honesty, here's a case where we have honest versus adaptive. Honest is blue, adaptive is red, or dishonest is red. This is the number of observations. This is the mean squared error. We picked a point near the boundary of our covariate space, a point with plenty of density, but just near the boundary. And we actually found that the mean squared error got worse as the sample size went up of the random forest. And that's because the more data you have, the smaller the leaves are that you put around points near the boundary, and actually the worse your bias gets. So the honesty can actually help even with mean squared error. So we show that these random forests do better than, the causal forests do better than KNN in terms of getting heterogeneity. And if you really want to show where the random forests do well, just throw a bunch of noise covariates at any method that is not adaptive. And those noise covariates will screw up the other methods, but the random forest can tell the noise covariates away from the ones that actually matter and continue to find treatment effect heterogeneity even in the presence of lots of noise covariates. Let me skip over this. So then what we did from there is we said, let's take this idea of the random forest and let's apply it to other methods, like instrumental variables, for example, or any method where you're estimating a structural parameter with GMM or maximum likelihood. And we realized that there were going to be some problems with that, because if I go back to thinking about the simple treatment effect picture, I'm estimating, it's pretty easy to go from thinking I'm going to estimate a mean in a cell to thinking I'm going to estimate a treatment effect in a cell. because the treatment effect is a difference of means. So it's not a huge leap to go from prediction to treatment effect estimation in a randomized experiment. But if I tried to estimate a complicated model within this cell, it would do very badly. And some of the more complicated models involve dividing by estimated quantities, like dividing by propensity scores or dividing by probabilities of being treated in an instrumental variables model. And so if I try to estimate these models in really small cells, things will go very wrong. And furthermore, my asymptotic normality theory required that I have deep trees with small leaves. And that would not work well if I tried to estimate a model within a leaf. So we realized we should rethink what a forest is. And we're instead going to think about the forest. I'm running out of time, so I'm going to jump to the main idea. We're instead going to think about the forest as a way to generate a weighting function or a kernel. So the idea is that we're going to build a bunch of trees, and those trees are going to be optimized towards parameter heterogeneity. You have to read the paper to see exactly how we do that, but we come up with a good computationally feasible way to build trees for parameter heterogeneity. But instead of just estimating my model within each leaf and averaging up the estimates, instead I say, OK, here's my target data point. I'm going to weight the other observations according to how often they ended up in the same leaf when I built trees that were optimized for parameter heterogeneity. And so then rather than trying to estimate the model and just average up the estimates across the trees, instead, I'm just going to use this as an intermediate step. I'm going to come up with a weighting function that's targeted for my parameter heterogeneity. And then I'm just going to estimate the model using local GMM or local maximum likelihood with this as a weighting function. So I might run my model targeting this point, weighting the nearby points according to what the kernel says. And we show that that works, and it's asymptotically normal. So let me now give an example. So I've got Josh here, and I didn't pick this just for you. This is the example that's in the paper. This is a classic fundamental pioneering paper by Josh Angrist about the effect of family size on women's labor market outcomes. So this is an example of the crazy thing economists try to do. We try to get the causal effect of having another baby. Obviously, we can't randomize directly whether you have another baby. And wait and see what happens 25 years later. But what you can do is look for natural experiments. And so at least before there was so much fertility planning, the gender of your child is random to you. And so it turns out that if people have 2 babies of the same sex, they are more likely to have a 3rd baby. And that is a natural experiment that increases family size. And so the instrument is having the first 2 kids being the same sex. That increases the probability of having a 3rd child by 0.06. Then we can look at what is the effect of that on the probability of work and your income. And what's called the local average treatment effect is an estimate of the effect of having an additional baby on the people who are influenced by this same sex. And it's just the ratio of those 2 things. So in his pioneering fundamental paper, Josh did a little bit of exploration of treatment effect heterogeneity, but being a conscientious scientist, he did not try everything under the sun, because then you would worry about false discovery and overfitting. But now I have a machine learning method that can do it for him, so if he wrote it today, he could just append another section to his paper that showed all the heterogeneity under the sun, because my robotic research assistant, that is my machine learning algorithm, found this for him. So this is what we find. So we look at the effect. So we estimate the generalized random forest model for parameter heterogeneity for this. What we're looking for is the parameter heterogeneity in the local average treatment effect. So we want to see for what kinds of people is having a 3rd child particularly impactful on their outcomes. Yeah, so they're all negative. I just made them, yeah. So they're all, the additional child reduces income and reduces participation. So what we can look here, and we can look at the impact of the father's income. And so there's a little bit of heterogeneity there. And this was on participation for, and this is for 18-year-old mothers who are 18-year-olds when they gave birth. This is for mothers who were 20 when they first gave birth, and there we see more of a U-shape. And so the idea is, like, if you're really poor, you have to work. If you're really rich, you definitely won't work. But the intermediate people are the ones who are impacted by this in terms of their working, which also tells you something about policy, because policies that target those people and have to do with childcare might be effective. And then we see even more of a U shape for the 22-year-old mothers. Now, the standard errors are pretty wide on this, and so this data set really isn't quite big enough to get a lot of precision on these estimates, but if I went back and gathered more data on this, I might be able to get more different effects. And so we have a theorem that says that this works and it's asymptotically normal. We also highly recommend residualizing, which is one of the themes. So I'm almost out of time. I'm just going to advertise another set of another part of the agenda, and then I'll conclude. So a final type of data, which I think is going to get even more emphasis in the literature going forward, is panel data. So I have a data set of consumers, and I'm looking at them shopping in a grocery store. That's one of my big data sets. I have a new data set where I've got mobile phones, and I'm spying on a percentage of Americans several times a day through their leaky apps. And so I have anonymized data of where people are. And so in these types of panel data models, I might have sparse behavior. So like you might buy tomatoes only 3 times in over 2 years, and you might buy paper towels only 6 times over a couple of years. But nonetheless, if I pool together the data of different people and your behavior towards different products, I can actually learn a fair bit about your behavior. So this has been exploited massively in the machine learning recommendation systems literature in something called matrix factorization. We haven't used this as much in economics. And so I have a series of papers now where I'm importing these techniques into structural estimation and causal inference. For example, I'm building discrete choice models where I use matrix factorization to factorize mean utility for agents as well as their, say, price elasticities, or in a case, their distance to travel. And I can use those matrix factorization techniques to do things like say, people from different places, are they more or less elastic to travel? And so I find a lot of heterogeneity in how far people are willing to travel. And I can also, once I have personalized estimates for people in restaurants, I can figure out where is the best place to put a restaurant. So those are the kinds of counterfactual questions you can do once you have a causal model. So just to conclude, I think that there's a huge amount of potential putting together the causal inference and econometrics literature with the machine learning literature. The causal inference literature thinks a lot about what do you need to have in the data to actually get a valid estimate of a causal effect, and how do you use those to do counterfactuals, like what happens if I change the price, what happens if I change the restaurant, what happens if a restaurant opens or closes, all those kinds of things, what happens if I raise the minimum wage. We have a lot of theory there, but our algorithms were kind of they didn't take advantage of modern approaches from machine learning. Modern approaches from machine learning are practical and high performance, but most of the mind share has been on predictive exercises. Cats versus dogs. Uses Xing to predict Ys, we can verify performance in a test set. So we've had to modify those techniques to settings where we're estimating a parameter or something that doesn't have a direct ground truth. And also, in cases we want to get statistical inference, confidence intervals, and standard errors, we found so far this has been very, we tend to beat existing methods pretty resoundingly across every single application. So my prediction is that going forward, people will just not use the old techniques anymore. They're going to use new techniques, and that will be pervasive within a couple of years in social sciences. And then from a machine learning perspective, this is a new area for algorithm development that hasn't received as much mind share, and I think it's a great opportunity. Thanks.